Hi, Mr. Tarindo. We wait for 5 minutes.
Okay, okay.
Okay.
Hi, can we start?
Yeah, we can start now.
Okay.
Please.
So last time we stopped at we stop at here after we getting out the voltage from the buck boost converter. Then that voltage will go to this OCP circuit. Okay, this entire
So become input. for this one OCP.
Yeah.
Mm.
So this one I will simplify. I will draw the schematic by simplifying. Before that one, let's identify the components here. Okay.
Okay.
So this is the OCP IC, and then we have a P-type MOSFET. Okay.
MOSFET.
Yeah.
Okay.
So it's like this. Wait, I'll draw the circuit. This is P-type MOSFET. This is the OCP IC.
Or P-type MOSFET.
You have to remember it's a P-type. It's very important. Before going to this one, maybe I will explain about the MOSFET also a little bit. How to turn on off the circuits using MOSFET. So this will be helpful not only here, there will be few things in the session. So for that one, it's better I will explain the OCP too. Not OCP, the MOSFET. Okay. Let's say we have a N-type MOSFET. So this is how we turn control a system using a N-type MOSFET. Okay, let's say we have a battery here. Sorry, I need to check something. Wait. Oh, I want to tell you something. This is not an N-type MOSFET. This is not a P-type. This is an N-type MOSFET. Okay. So,
how to differentiate if I say just look from here, can we differentiate from the circuit?
wait. Yeah. Actually, we cannot differentiate by looking at from here. So we need to go for the data sheet. I will explain that one later after I explain in this MOSFET cases. Okay.
All right.
So first one is N-type. Let's say we have a battery and we have some kind of load. Let's say load is like some filament bulb. So if we connect like this is the circuit we are going to use. So the N-type MOSFET will have something like this. So if you don't remember the mark, how to put this one, so N-type has the arrow inside. So the way I remember is arrow is inside, in. So if it is in, that is N-type. That's how I remember this one. Okay. Then then we connect the like this, and you need to remember there is something external, not external, internally created diode is there. So this is the symbol for the MOSFET. So if this is gate, this is source, this is drain. So to turn on this MOSFET, this we call VGS. If we turn on the MOSFET, LED will turn on. Okay. So this VGS is equal VG minus VS. Okay. So this is VG and VS are the nodal voltage of here and here. So since this is connected to the battery, so we can define this as ground and 0 volt. So Vs is 0 volt and Vg is like this. Okay, to turn on this MOSFET, turn on means to conduct some current to this direction. So we need to make this value greater than some constant value, constant voltage. So if you check a MOSFET graph, MOSFET characteristic, we put VGS into this axis, the ID, that is the current going here, we will have a plot like this. So after certain voltage, actually after certain voltage, it will start to conduct. So that is where I said K. Okay, understand? Okay, if I go back into some N-type MOSFET, this is yeah, this is N-type MOSFET. You can see this is not this MOSFET, it's a different MOSFET, but anyway, you can see here after 1.2 volt of VGS, it will start to conduct very huge current. So which means MOSFET is on. So if you go here in the data sheet, if the VGS is 1.8, it will give 0.02 ohm resistance here. So which means that's all is almost kind of like a conductor here, because very small volt or resistance here. Otherwise, if you can see somewhere here, you can see less than 0.6 or 0.9 is not so good conduct. It's not conducting better. So the thing is, if you increase if the VGS is more than that voltage, as example, let's say K, this K is example, okay, 1 volt. If you apply more than 1 volt here, so this circuit will turn on, this bulb will turn on. Basically, you can take this voltage and can do like this. So it's a toggle switch. If you flip it, if you close it, there will be a current. Okay. One more thing you need to remember, in MOSFET, let's say you close the circuit and open like this. Bulb will not turn off because this is kind of like a capacitor, because gate if when you close it, gate will charge to the voltage here. When you remove it, you are not discharging, so this gate will have a non-zero voltage, which means it will be keep conducting. Okay, to avoid that one, so you can pull down this one using a little bit higher resistance like 10K or something. When it is closed, so this voltage will be positive, so MOSFET will turn on. When it is open, since there is a resistor here, it will discharge, so circuit will turn off. Okay, that's how N-type MOSFET are used to control the circuit and some kind of load. Okay, this MOSFET can be placed in a different place also. Instead of here, what I can do is I can place it here. Okay, so let's see that case. So the second case is N-type, still N-type. So what I'm going to do is I'm going to place the MOSFET in upper position. Since this is N-type, this one goes inside. Okay, so then now you have the bulb here. Okay. Actually, this is the arrangement we have in the satellite. So if you go here, maybe I'll make sure this is N type, okay, before explaining. Otherwise,
It's okay, no worry.
yeah, it's the N type MOSFET. Okay, I will show the. Maybe I'll share that screen. Yeah. You can see here. This is SSM 6K14. This is a N type N channel MOSFET. Okay, so you can see it has 4 drain pins. Actually, there are no 4 drain pins inside, just one drain, so which is connected to 4 pins. Okay, it's like that. So we have the circuit like this. So here is the gate, here is the drain, here is the source. Okay, so let's say, as an example, let's say this is 5-volt battery and this is ground. Okay, imagine a case where previously I said this VGS should be greater than, let's say that K value is 1.21 volt as example. Okay, should be greater
Greater
than
than 1.
1
Must be
volt. Okay,
greater than 1.
yeah, it depend on the MOSFET you select. Okay, it can be different value, but for the explanation I assume it is greater than 1. Okay,
Okay.
so let's say someone do the same circuit like previously. Okay, now what will happen? So here is 0 volt. So VGS I will write like VG minus VS. So since there's initially it's not conducting, since this 0 volt will appear here. That's the electrical, in electrical theories, it's kind of like that. If 0 volt, this will appear here. So which means this VS will become 0 again. Okay. Now when we close it, when we close the switch, now our VG will go to 5 volt. Okay, now VGS is 5 volt minus 0. So VGS is greater than 1 volt. Okay, now there will be a problem, because if that is the case, this will turn on, which means we will have almost 0 ohm resistance here. Okay, which means 5 volt here will appear here. So Vs become 5 volt now. Now there is a case, a contradiction. VGS is 5 volt minus 5 volt. So which means MOSFET is not turning on properly. MOSFET will keep some voltage drop here and it will have 4 volt or something to the load. So that is a problem. So which means using this kind of arrangement, using this battery, we cannot turn on this MOSFET correctly. So the way we need to do is we need to apply more voltage than 5 volt. So basically, what we need to do is we need to add another battery set. Maybe let's say 7 volt or something. Then no issue because VG will be 7 volt. After turning on, VS will be 5 volt. So there will be 2 volt VGS. So the thing is, this kind of case, you wanted to turn on this bulb, but the problem is you need to have another power source, which higher voltage. This is kind of is annoying to have this kind of system. If you go back to the previous case, using this method, you can turn on off the LED, but remember, you are cutting the ground, okay? You are not cutting positive side here, okay? Did you understand that one? Battery positive will apply to the your load. You are only cutting the ground. But the advantage here is you are cutting the positive side of the battery, okay? But the thing is, adding little bit higher volt gate driver kind of hard in a case where you turn on off a LED bulb or something. But in our circuit, we use this method, okay? Our OCP chip generate little bit more voltage to drive the MOSFET. So if we go here, this is our circuit. This is how it happens. So I will draw the circuit here again. So we can assume this buck boost converter as a battery, okay? I will replace the buck boost converter using a battery. So then our power comes this direction, okay? That power goes to this shunt resistor and it goes to this MOSFET and current will exit from here, okay? This is how it happens. So we have very small shunt resistor, this 0.025. Okay, let's forget about shunt resistor case, okay? I need to explain that one again. So what happened is we go, I said power comes here to this MOSFET, okay? So that MOSFET is like this, N-type. So it goes the load. This side is the load, okay? Load, whatever payload you will have. Forget about this current sensor. It's kind of like it's like nothing, okay? For now, we connect it to some board somewhere. So we have the load here. Okay. So I said this mod, if the arrangement is like this, since this is 3.3 volt, so this gate voltage should be greater than 3.3. Is actually so then we have the OCP IC. You can see here there's a gate driver comes here with the capacitor to generate little bit higher voltage. So as I remember, it's about 6 volt outputting, okay? So if the OCP output 6 volt, so this circuit will run without any issue. If the OCP output 0 volt, this will be cut, no power going to the load, okay? That's how we control the power, okay? Understand?
Yes.
So now we will see how the this OCP triggering happens. This is how. So the OCP trigger. So I replace again buck boost converter using 3.3 volt battery, and there's a very important resistor here. So that is the shunt resistor, this one. Okay, so very small value, like you can see 0.025, 0.025. Then I will draw the MOSFET like this. Okay, I will not going to draw the complete circuit. Oh, but I draw actually. I will draw the MOSFET this orientation. Input. And our load is some kind of board. Okay, this is the circuit. So what this OCP chip does is very interesting thing. So let's say I forgot some value, so I need to see something. Okay. So there is a voltage measuring. Maybe a little more. We have the OCP IC here. It measure voltage drop across this resistor. Okay, V drop, or we can say V sense. It measure voltage drop across this resistor. Okay, you need to remember this current coming to this direction almost zero. Okay, very small, like very small nanoampere current coming. Okay, you have to remember that one. Both lines are not taking too much current, it's just sensing the voltage. Okay, so then we have, as I told you before, we have the gate driver pin. So when there is a current going in this path, we will have a, we can write that current will exit from here, I. Okay, since I assume this path don't have current, if according to the Kirchhoff law, if the current goes here I, output will be also I. So then I can write this V equal IR equation for this V sense. Okay, so V sense is equal
0.
0.025. Okay, understand? But I'll make this one as R. Okay,
Okay.
for the simplicity. Okay, in this, it's actually there is some kind of inside there some kind of op amp and to detect those things. Okay, this OCP says if V sense is less than 50 millivolt, this gate signal will be high. High means about 6 volt. Okay, high. Else V sense is greater than 50 millivolt, gate voltage will be low. Okay, you understand this condition?
Okay, I understand.
So now you can see, if you put a constant resistance depending on your current flowing in the system, you can see this gate signal will vary. Okay, for the example, I'll take this R value. So V sense I put 50 millivolt. 50 means 0.05 volt, and 0.025 is the R value, like this. So I is 2 ampere. Okay, understand that one?
Yeah.
So which means if according to this resistor value, if the current is 2 ampere, there will be 50 millivolt drop here. If you exceed more than 2 ampere, this drop will go more than 50 millivolt, which means you can see here gate will be driven to low. So that will be cut off. Understand? That's how this OCP works. If the current is less than 2 ampere, so this V sense is less than 50 millivolts, so which means this case. So gate will be high, this MOSFET is on, no issue for the current to flow. Okay, understand?
Yeah.
That's very simple. This is how actually OCP works. But there's one drawback here. You can see here there is a very small drop happen. So which means you will not, if you have 3.3 volt here, you will have output 3.3 minus some value. This X value is less than 50 millivolt. Okay, so which means like very small drop will happen. So you have to ignore that one. Understand? This is how OCP works in our circuit. So this is drain, this is source, this is gate. So no issue. If you have a question, you can ask.
Okay.
Okay.
Meaning the current clear very important.
Yeah, actually, now you can see by changing the resistor value, you can set the OCP triggering voltage current.
Yeah, yeah, you're right.
So you can see here. So V sense, you always know V sense is the 0.05, and then let's say you want 1 ampere OCP triggering. So which means you need to put R. Then you have to calculate R value. R will be 0.50 ohm. If you put 0.50 ohm here, you change the circuit to 1 ampere OCP triggering. Okay. If you want 4 ampere, but 4 ampere case is kind of like a meaningless because this guy cannot provide the 4 ampere. But if there is a 4 ampere buck boost converter, you can change it easily. Okay.
Okay.
So actually, let's see the 4 ampere case. So which means same equation 0.050 4 ampere is R. So you will get R value 0.001. No. You will get 125 ohm. Okay. Maybe you will not be able to find this one. What you can do is put another 0.025 ohm resistor parallel to this one. Then it will increase to 4 ampere because the resultant resistance will be this value. Understand?
Understand.
Yeah, very easy. Like there's a freedom to change this one. Okay?
Yeah.
So now you can see the circuit. Now you will understand. This is our MOSFET. So the current path is this shunt resistor and goes through this one. Okay. So you can see these are the voltage sensing pins for the OCP. Okay. So then I said we can enable, disable the OCP. Okay. So you can see here using this pin we can enable, disable the OCP. But you have to remember there's something you have to see. There's bar here. So which means if
Low
the
means activate.
both pin 0 okay, 0 means on, 1 means off. Okay, yeah. So basically, okay, imagine case where we don't have this part. Okay, imagine case where we don't have this part. To turn on this one, we from microcontroller we have to make this pin low. Okay, and turn off this pin high. It's kind of like not the it's not matching. Normally when we say on, it is 1, off, it is 0. To invert this logic, we will use this NPN transistor. Okay, if we make it 1 here, this will be 0. If we make it 0, this will be 1. So I said on, off. So now you can see in the logic you map 0 to off, 1 to on. Understand? So what I mean?
Yeah,
If you-
yeah.
Yes, yes.
So basically inverting the logic coming from the pick. So let's see in this path where this line goes. This goes here, 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 and it again goes to the this pick. Okay, understand?
Yeah.
But you can see there are no 1K resistor.
Mm.
Reason is this transistor, if I zoom it, it's a Darlington, it's not a Darlington, it's a pre-bias transistor. It has internally that resistance. You don't need to worry about the adding. This is, as I remember, 47K resistor. So it's pre-bias resistor. You don't need to do more protection because it internally is protected. Okay. So that's how that happens. Okay. Then let's come to output of the OCP. There is we normally place a capacitor after some kind of turning on off to avoid some voltage fluctuation or filtering the noise. Okay, that's why we have this capacitor. Then we go to the current measurement circuit. Okay, similar to previous time, there is another shunt resistor. Okay, whatever current comes, it goes in this path. You have to remember there's no current going to this path. Okay, it goes like this. So let's see how this current measurement circuit works. Okay, let's say someone tell you, okay, make a circuit to measure current. So without using any chip. So the easiest way is this one. Use the shunt resistor again. We have a battery. We have a battery. And we have the load. We don't know what is the load. And we need to measure the current going in the circuit. So the easiest way is you put a resistor. So R. If you measure the voltage building here V by, then you can write the equation V equal IR. So then V divided by R is the I. So then since you can measure the V is measuring and R is known value, you can tell how much current going in the circuit. Okay, but let's say someone use R like 10 ohm or something. So let's imagine a case where our load also around 10 ohm. Let's say voltage of the battery is 10 volt. According to this case, load will receive only 5 volt because this is kind of like a voltage divider. Okay, voltage will be divided equally. So this is not good because we need to have we need load to have the 10 volt. Since what we do is we can reduce the R value. We can go very small R value. Okay. Now the thing is, if you reduce the R value, you can if you reduce the R value, you can see according to this equation. Okay. Your voltage will also go very low for the constant current. So it is harder to measure. So then what we can do is we can amplify that voltage and get some measurable voltage. According to that one, we can give the current. We can tell how much current going inside the circuit. The similar way is used here. Okay. So you can see here 0.025 volt shunt resistor is used. So the current goes in this path. This is a op amp with some gain inside. It will output a measurable voltage here. Okay, depending on the current. So the data sheet has provided the equation. Wait, I need to find the equation. This is LT6106. Okay. Equation is this one. Let's say if the current is I, if this shunt resistor is Rs, so it has provided this is V out. Okay, this V out is equal I times Rs times R out divided by R in. This is R in. Okay, this is R out. So you can see by changing your R out, R in, this Rs, you can have a proper voltage output. Let's do the calculation for the values shown here. So V out will be I, Rs is how much? 0.025, and the R out is okay 4.95. Okay, let's say it's 5k. Okay, it's 5,000 ohm. Then the R in is 100 ohm. So I is how much? Oh my god, 625. How much is the standard? Someone tell me what is the value here? 50 multiplied by 0.25 is 1.25. Okay, V out. So which means if there is 1 ampere current going in the circuit, what is the voltage we see? V out will be 1.25 volt. If 2 ampere going, V out will be 2.5 volt. Okay, did you see? Understand? In between values of let's say 0.5 ampere goes, V out will be how much? 0.625 volt. So it's a linear relation. So then that voltage output will go to the one of analog input pin of this PIC. PIC will measure the voltage. Depending on this relation, we can get the current flowing in that path. Okay, understand? If you don't understand, please tell. Okay, so you can see the sensitivity of the current. If the 1 ampere goes, it will show 1.25 volt. Actually, this one 1 ampere go 1.25 ampere.
Yeah, can see.
Yeah, it's very simple. And then again we will do some filtering and give power to the system. That's how we give power. Very simple. Understand? Okay. Then let's go to the 3.32 line. So I don't need to explain this one because exactly same here. Here same.
So
And
for the 5 volt and regulator, all are same, right?
yeah, I'll explain that one. Huh? So this one same, everything same. Okay. Now let's go to the 5 volt one. It gets the power from the raw voltage here. So it's a different chip, okay? Because this is a boost converter. So you can see this 5 volt chip input should be 2.3 to 5 volt, okay? So since this voltage, okay, there's a issue in this 5 volt case, okay? Because our voltage will vary from 2 volt to 4.2 volt.
Yeah.
So at 2 volt, 2.1 volt, 2.2 volt, this boost converter will not work properly, okay? So you have to see those conditions. You should not operate some system if the voltage drop below certain voltage, okay? So this 5 volt chip don't have a feedback pin to control the output voltage. Basically you just need to feed the, so here it's not mounted, okay? Just need to, this is 0 ohm, just need to feed the output to the feedback, okay? So it will give 5 volt output. But I will suggest something. If you want to change this voltage, this one is 61235 is the number you can see here. This one is the
Yeah.
So I'll draw again. There is a is it, what is it? 35. So there's something you need to know. This is our feedback pin, output feedback pin of the IC. So we have an internally kind of buffer. So in, what is the number? 61235. 61235. You don't have the voltage output voltage control option, but this one has the option. So in this chip, internal arrangement is like this. So it is connected here. The voltage divider mounted inside. So you just need to give the output voltage. Okay, but 61236, it is connected to here. Basically this is kind of like not there. So then you can create a external divider and connect it here. So this equation is R1 R2, this is TPS 61236. Okay, that then V out, this is V out. V out is 1244. This is the equation. So just remember, in this chip you cannot control the output. If you want to control the output, use this one. Okay, that's the bottom line. Okay, again, so you can see here input filtering, output filtering. So you can see we use for 22 ohm, no 22 UF capacitors, but here only 3 because it's the datasheet suggestion. And then again you can see that chip enable line here going to the peak, and then so then we again have the same OCP. Okay, you can see same, sorry, same 2 ampere same 2 ampere OCP triggering volt current, and then same circuit. Okay, and then if we come here again, we have the same current measurement circuit. Okay, this is independent from the voltage. It's independent from how to say, the voltage of the line. So these circuits, it's just check the current only. Okay, then we have the unregulated line. So same raw power line comes here, goes to the unregulated OCP only. It don't have the any buck boost converter. So you can see the logic inverter here, logic similar to previous case. Now you can see the OCP. OCP is 4 ampere. Now you can see the way it was changed. Similar to the last method I said. So now the resultant resistance is 0.125. So since the OCP triggering current is 4 ampere. So in this path, OCP current can go flow more close to 4 ampere. Okay, maybe this one. Okay, one more thing. There are mistakes in this circuit. Okay, this was one of initial circuit. Please remember, in the 5-volt line, you have to take out this resistor. Okay, take out means directly solder it. So it was a mistake in the circuit. So and here there's another mistake actually. This circuit we need to recalculate the measurement. Okay, let's see the problem here. Okay, this is how you debug if you have a problem.
Sorry, just now you said the for the 5-volt, I need to remove that one R23, is it?
Yeah, R23. You have to directly connect.
So there is no voltage divider.
No need voltage divider there because
Okay. All
yeah,
right.
it's similar because you saw here you are measuring only maximum 2 ampere.
Right.
So at 2 ampere, it gives 2.5 volts. So you don't need a voltage divider because
Okay.
our ADC, I forgot to tell, our ADC reading range should 0 volt to 3.3 volt. Okay, it is 2.5 within the this range. So then we don't need any voltage divider here. It was a mistake actually.
Okay.
So now here is another mistake happening. Okay, so let's see the problem. So let's write the V out again. This I'm writing V out here. Okay, not this place. Okay, that is the equation given. V out, what is it? I R S R out R in. I miss here. I R S R out R in. So I is okay. Let's keep the I just there. RS is Sesi 0.025. R out. Remember, this is very important. R out is not this one. R out is this entire path. So which means about 7K. R in is 100. So then I, let's see. Zero point 0.025 multiplied by 70. So 1.75. Okay. If 1 ampere, V out will be 1.75 volt. If 2 ampere, V out will be how much? 3.5 volt. If 3 ampere, V out will be 1.75 multiplied by 3 is how much? 5.25.
Yeah.
And 4 ampere, V out is 7. Okay, you agree with these values? Okay, no issue. But there's the issue here. Okay, you can see if 7 volt volt appear here. No, let's say 7 volt appear here. Less than 7 volt will go to the measuring circuit. Okay, but the thing is, this chip cannot make 7 volt because chip is powered using maximum 4 volt. This voltage vary from 2 volt to 4.2 volt. So this chip can only provide the voltage to similar this. This is unreg. Okay, it's not any buck boost. So let's say you have the maximum voltage case. Maximum voltage it can output is 4.2. It cannot have this one. Basically, it's saturated. You know, when you have the gain of PAM, gain is value is increasing. After some time, it will saturate. It cannot go more than that voltage. Basically, this is the supply voltage. So this calculation is wrong. So actually, it was a mistake we did initially. So we forgot actually here out input voltage is this one, and then we need to do some different method here. We need to aim something like this. Let's aim when the 4 ampere goes 3 volt output. Okay, so how do we do this calculation? So what we do is we take the same equation, we put the V out 3 volt, and then I is 4, RS is, okay, since let's keep it this value, and R out and R in. You can see by adjusting R out and R in, we can get a 3 volt at 4 ampere. So then we have two variables here. We have to make one constant, otherwise we cannot come into a conclusion. If both are varying, okay. Let's do something.
So make it I mean R over R in, make it the ratio 30, is it? Just make
Yeah.
sure they can get 30, then we can
Yeah.
vote already.
Yes. So you have to select a ratio which can give this, which can satisfy this equation. So normally, let's say we set R in like 100 ohm. If 100 ohm, how much is the R out? I need to calculate, okay. 100.
3,000. Is it? No, wait.
3000?
Wait.
Yeah, it's 3000 actually.
3,000.
You need to put 3K resistor there. Please remember this one when you use this OBC, okay? If R in is equal 100 ohm, R out will be 3000 K. So basically, so ratio should be 30. R out divided by R in should be 30. You need to find some resistors to satisfy this one. If you cannot find 3K resistor, maybe you have to change the R in and get the R out according to that one, okay? But you can, maybe you can find 3K. So the circuit will be like this. There will be no resistor here. It's directly connected. This resistor is 3K. And then if you go here, this OCP is 3 ampere. Okay, we can aim the same case again for this OCP. I connect this one again. So let's see. My aim is getting 3 volt when 3 ampere goes, I need 3 volt output. So the same kind of case. So 3 volt, 3, 0.025 R out divided by R in. So we see this cut. So this is 40. So here you need to put 4K resistor. Okay, understand?
Yeah, understand.
So is it correct calculation? Did I correct?
Yes.
So this is basically 1 over. Please make sure I'm not sure. I just did. Yeah. 4K. It's 4K. Understand? Any question?
Yeah. May I know after this, just how you say it connects to the one, the what PSC 16F. from here until
I did not hear it properly. Can you tell me again?
I mean after this after the sensor, so there is a line connect to the PIC.
Yeah, pick here.
Yeah.
Then you can measure it using this one.
Mm.
Yeah, very simple. Okay. Basically, every analog line goes to the. You can see here, 100 guys sense, 102 sense, 101 sense, 5 volt sense. Everything goes there, and we can measure it here. So this is very, very important. You must measure this one in some interval. Okay, in burst 3, every 90 seconds, reset pick measure those current and save in the flash memory. Those are the housekeeping data. Okay, very important things. So any question? Any other before I go to reset pick? Okay, can I go to reset pick now?
Yes.
Okay, let's see the pick. So if you, maybe I have to go through every pin. Okay, let's start from number 1. This is UART RX pin. Okay, you can see this one goes like this. This goes to some kind of, actually signal comes from COM peak. You remember I told here there are UART line connected here. So UART has 2 lines. So one comes from COM peak and it goes to this chip and it comes through here and comes here. Okay, you understand this path. So this is a buffer. Very important thing, this one. We need to put a buffer. I will explain why. If you take the config, let's say config here. And we have the reset bit. So this TX will be connected to this RX. Okay, that's very simple if you do the UART connection. Okay, but this is not a good way of doing, because not sometime, always. So UART is normally high. If you draw a plot, UART, the TX line is normally high. That is actually 3.3. When there's data, it's just do some flipping, not flipping, like this kind of signal, and go back to 3.3 again. Okay. So there is some problem in the this peak actually. Even though, let's say, reset peak don't have power, if there are no power, if this COM peak is on, this TX line will power the reset pick and make it on. So that is not good, because you have to turn off some pick. Actually, reset pick is always running, but the other way around it will happen. Let's say in this direction, this TX line is always high. So let's say reset pick turn off the home pick. But since this one leaking power to the config, it will not turn off. So it will be running. So because of that one, to avoid that situation, what we do is we put a buffer. and we have the reset peak. So this is Tx, this is Rx. We have a buffer at here, and we have a buffer close to this peak. This has the 3v3 reset peak power line. This has the 3v3 comp peak power line. We power this buffer using 3.3 comp peak, and this buffer using 3.3 reset peak. Okay, so let's see. When reset peak turn off the comp peak, it will turn off this 3v3 comp peak power line, and it will basically, this also will be turned off, which means whatever happened here, 1 or 0 will not transfer to this direction, which means there will be no power leakage from here to here. So that is one way of protecting. Okay, so here also there will be no, but here meaningless because this reset peak will not turn off, but here it will be meaningful. So there will be no power leakage. Understand?
Understand.
So if you see every part of the OBC, you can see a buffer closer to the RX pin of that IC. Okay, let's see that one. So you can see the data line comes from comp peak to reset peak. Actually, this path. Okay, there is a buffer closer to, this is the buffer. It is powered using reset peak power line, and the data line coming from main peak also goes to the same chip because this chip has two buffers inside. So we don't need to use two different ICs, so we can use, say, other buffer main peak line. Okay, so this is the data line goes to the reset peak to comp peak. So if you see the data big one, if you go near the reset peak, no, go near the comp peak, you can see the reset peak to comp peak line has its own buffer at the comp peak side. So it's similar to this one. You will understand when you see it. Maybe you will not clearly see when you first time see. You have to remember there are buffers near the its own near the peak ICs. So then those are the UART line goes to different places. Then you can see here RD6 and RD7 are the comp peak power enable line and main peak power enable line. If you want to turn on the main peak, you have to first program the reset peak to enable this line to 1 and enable this line to 1. If you want to turn on the comp peak, you have to make this line 1 using this reset peak. Okay, otherwise those peaks will not be running. Understand?
Understand.
Yeah, before I go there, I forgot to show this is before, these are the no. You remember I showed this one, power supply to reset peak, comp peak and main peak. So it's here in the circuit. So exactly same.
This is in another picture.
Yeah. So raw power, this is the reset peak power line and comp peak power line. These are the OCPs actually, OCPs, main peak power line. These are the two lines I just explained before. Okay, comp peak enable, main peak enable. You have to see, it's very important thing here. This one is not a huge current OCP. This is a 50 milliampere OCP. Previously, it was like 2 ampere, 4 ampere, something like this. Can someone explain why this low current is there? Comp peak only uses 100 milliampere. Main peak only uses 3 300 milliampere.
Saya semangat selalu macam ni benda.
Can someone say why this reset peak
Saya rasa ni
is
kalau
only 50 milliampere? Okay, I will explain. Okay, listen this one very carefully. So, if you get the reset peak,
kalau ni saya lah selamatkan dulu ni kat atas tadi je lah supaya saya follow up, saya buat tindakan ni. Nanti edit benda ni saya pergi.
sorry, I get little. Okay, if you get the reset peak, in nominal condition, peaks consume about 20 milliampere. Okay, so which means 50 milliampere is no problem. There will be no OCP triggering. But have you heard something called single event latch-up? Single event latch-up are when the protons and those things hit the ICs, internal gates, transistors turn on automatically. At that time, huge current will go through the IC microprocessors. It will be like 200 milliampere, 500 milliampere, or something. That's huge for a IC because it's the nominal current is 20 milliampere. So if this kind of situation happen, it is greater than 50 milliampere. So which means reset peak will be turned off using the OCP. The reason we set the 50 milliampere value to protect from single event latch-up case. So that's very important. In the space, you must not set this one to 1 ampere or something. If that is the case, if the single event happen, your reset peak will be destroyed. Then your entire satellite will be gone. Okay, you have to remember that one. You should not exceed this one. You have to remember reset peak OCP settings. And then if you go to the config power supply, it is 100 milliampere. It's still less than the this single event current. It needs little bit more current because it needs to run some flash memories, and there are some chips to run. And for the main peak, we set 333 milliampere. So this one is not so good setting, but we have to use because if you want to reduce, you can reduce it. We had to use because we need some current capability in that power supply. That's why we set it to 333 milliampere. So basically, it's like that. I'll go back to the reset peak case. Okay. So then, wait, I need to drink some water. Then we have the VSS, that is the ground, and VDD, that is the 3.3. And these pins are not used. If you want, you can use it. And then we have something called WDI. Okay. Have you heard about external watchdog timers? There's a very important thing I need to explain right now. It will take some time, but you have to understand, okay? Watchdog time. Then you can understand what is the meaning of this part. This part you will understand when I explain this thing. Watchdog timer. Okay. Okay. If you get a PIC IC, it has internal watchdog timer. PIC has internal WDT, watchdog time. What it does is this one. Let's say, okay, let's write some code here. Normally, you will have a white main loop in C. Okay, this is C. Then you will have a while true. That is the continuous loop. So you will have line A executing some function, line B executing some function, line C executing some function. It goes like this. In nominal condition, this will run, this will run, this will run, and go to the end and come back again. This will run. It will be looping like this. Okay, that is the normal operation. What if someone who don't have experience or someone make a mistake in this line B? This line B. If the code is stuck here, there will be a problem. Entire code is not running correctly. So the code is stuck here. Now pick is also stuck there. Nothing is happening. So just stop there. So what watchdog timer do is, watchdog timers, if the watchdog timer see this kind of a stuck case, it will reset the pick IC to run normally. But if you have a problem, a big problem here, it will always get stuck here. But when you do some calculation, some wrong value, let's say when you do a calculation, some wrong value make this condition true, which means stuck here. When you get the correct value next time, it will run correctly after resetting. Okay, so which means watchdog timers save the peak from this kind of stuck case. So this is internal watchdog timer. The way it happens is like this. At the every loop, you have to restart the watchdog timer. Watchdog timer tell us, okay, you have to restart within 2 seconds, within 4 seconds. We can set those second in the code in the beginning, 16 seconds, 32 seconds, something like that. So what happened is, let's say we set the 2 second case in the code. When the code running, no, it was normally running. Coming here, it reset the watchdog timer and went here and reset the watchdog timer. And next time it got stuck here. Let's say it stay here more than 2 seconds. So which means this code did not run. Watchdog timer see it more than 2 seconds. It will restart the pick again. So that's how it happens. We can set these delays. How many times need to be wait. Okay, did you understand that?
Okay, understand.
So this is internal watchdog timer. What if that watchdog time also got stuck? It can happen when the single event latch up case happens. So we had to protect this pick go into this case. So instead of using internal watchdog timer, we can use the external watchdog timer which has resistance to those radiation. So that's what we have done here. Okay, so the way it happens like this. So we have the PIC IC. You remember I said there is a MCLR pin. We must pull this up 3.3 volt. And we have an external watchdog timer IC. What is that? So it has WDO pin. It is connected to here. And then we have WDI pin. It's coming from the PIC. I don't remember which one. That is RB2 pin. Okay. RB2 pin. This is a 1.6 second WDT, watchdog timer. So this is how it works. Similar to previous case, void main while I'll just put one instead of true. We have the line A running, line B running, line C running. So at the end, we need to make sure this output high B2 and then output low B2. This is how we restart the watchdog timer. Again, similar way, this will run, this will run, this will run. It will come here. If you toggle the RB2 line, B2 line, this watchdog timer will do nothing. So watchdog timer will keep outputting 3.3 volts. So you can see still this place is high. If this one get stuck somewhere, this place, these two codes will not run. So if that stuck time is greater than 1.6 second, this external watchdog time was not resetted, which means this will make this light low and keep it some time. After some time, it will take back to 3.3 volt, which means this guy will reset it. Okay? Understand? You have to toggle the B2 line when in the normal operation.
How do you test manually?
Okay. You can introduce a delay here. Put a delay, 2 seconds or something. You can see it keep resetting. Very easy. That's a good question actually. You should not take too much time when you run these codes, okay? If it is greater than 1.6, even though your code is correct, your PIC will get resetted. Okay, this line should run very fast. Understand?
Meaning if I say put too much code, it takes too much time, more than 1.6 seconds, is it?
Yeah, that is dangerous. So make sure it finish within 1 second or something, okay? Everything. Normally it's very fast, no need to worry, but you have to remember you don't take too much time when you run these lines, okay? Whatever function they are. Because it's 1.6 second only. You have only 1.6 second for one loop. And don't set it exactly 1.6, okay? That's a dangerous case. That's why I said, imagine your code, this loop take only 1 second. You are safe. You have better margin. Understand? So, any question? This is very important. You have to remember. Okay, let's go.
About the limit current in the previous circuit. Do you have to test every time the
Which one?
I mean
Current
the limit current, the like the
OCP?
OCP, yes.
Yeah.
Do you
When you
test?
I forgot to tell you actually some test, okay? When you get this circuit, please connect a load here, okay? Variable load. Have you seen the electrical load? Do you
Yes.
have so connect the electrical load. You can change the current. You can see how much current going inside, and you have to make sure at close to 2 ampere it turn off. Okay.
Okay. Okay.
So sometime if these resistors are wrong, it can go 3 ampere or something. So you have to make sure it is correct. Sometime it trigger at 1 ampere also. It's if there is a problem in the circuit. So you have to correct those things. After you get the boards, you must check each and every power line. Okay.
But we need also to isolate the load during the taking.
Yeah. Just plug the. What you can do is it's very simple. I'll show how to do it. Okay. So plug the OBC in the back plane here.
Mhm.
Okay. You give low voltage power line through a jumper here. You don't need a battery.
Mhm.
Then what you can do is somewhere here, as example, this is 5-volt line. Put a jumper and connect it to load and get the ground also.
Okay.
You don't need other boards actually.
Mhm.
You isolate everything.
Remove the payload.
Yeah.
Remove the-
Actually, yeah. You take out the payloads. Your payload is now electrical load.
Yes. Okay.
Okay, let's come here. This is the watchdog timer chip. You can see here we have that input signal line goes to the WDI. Okay, and WDO output goes to where it goes to MCLR here. Understand?
Yes.
This is the small connector I told you before. Using this connector, you can program the peak, because you can see PGC is connected, PGD is connected here, MCLR also somewhere connected here, and ground and 3.3 everything there. So you can plug a connector here and do it. Okay. So there's something else here. This one is a bi-directional kind of buffer. I will show. This is used for the PGC and PGD. If I go here in the notes, I told you before how to program four different peak using a small number of lines. Before connecting here, this chip will be there. So there are some buffer ICs put in the PGC and PGD line. So that is what here before coming it outside. So you can see this is the PGC. It goes here 2A. It goes to 2B and PGC comes out. Okay, it's a kind of buffer. And then PGD comes here. PGC goes to this 1A, 1B, this path. Okay, it's basically a buffer. Okay, don't worry about that one.
Okay.
You since these things are together, you will see like, oh, this is complicated. No, it's not together. You can see only. Let's take the 3.3 power line. That's why you see this as together, and use the same ground. It's basically two different circuit, very close. Okay, understand?
Yes.
Yeah. So what I can do is actually, I don't know need. So if I can, sorry, I can not here. I can erase here, erase here. So it's like that. Okay, no need to worry. I just keep it. You will understand. I don't need to erase and keep it. Okay.
Okay.
So please someone be familiar with this reset pick. You must do it. Okay. If something simple mistake here can cause the satellite to not to work. Okay. Okay, there this side, okay, PGC programming. These are the analog lines coming here, and then we have another thing here. This create that clock. That let's see, wait. That is 2 to the power 32, not 32, like 15. This create 32,768 hertz signal. That synchronization signal, it goes to the reset peak and every other peak. Okay, so using this frequency we can create a very accurate 1 second pulse to create RTC, real time clock inside. If you divide this signal frequency by 15 times, you will get 1 second delay. So that's how this peak create 1 second delay inside. So using that one, you can create a timer inside. Timer means you can have hour, second, minute timer. Okay. So then we have the crystal. This is clock source of the IC. This is a 16 megahertz crystal. So this chip can only support maximum 32 megahertz. You don't need 32 megahertz for this one. Please don't change the crystal, okay, if you want to use this one. And then we have the VDD, VSS, and there's actually this one is the next important thing. These are just current sensing. Those are going to, so you can see AN pins. Okay, AN pins means it can measure current. So analog ports. So there's one important thing. You can see something here. This raw voltage monitor on, and this one. So I said here, this is raw voltage line. So we need to measure the raw voltage line using the we need to measure how much voltage in the raw voltage line. So because of that one, we need to connect raw voltage line to peak to measure. That is not a good method because some current can flow in this path. Because raw voltage is a different way, it's a bus voltage. Preset peak uses a different power supply after buck boost converters at the end. So you should not directly connect it. So because of that one, we connect it to a kind of buffer. When we want to measure only, we will enable that buffer. So you can see raw voltage monitor on. If we make this pin high, you can see this voltage here. Okay, then you can. But the problem is you cannot connect that voltage directly because it can measure. It can go to 4.2 volt maximum. So our ADC reading measurement range is 0 volt to 3.3 volt. So because of that one, you have to divide into half. So then we can measure. Did you understand? Basically, we isolated the raw voltage from the reset peak. If we need only, we enable and measure. Okay.
Okay, okay.
So please remember why we use this one. This divider, because peak cannot measure more than 3.3. Okay. One more thing. I hope you guys know this one, but I'll tell. Let's say if the peak detect here voltage is 1.9 volt, which means row voltage line is 3.8 volt, because half of the voltage from here will appear here. Okay. So any question?
Hmm. So there is a coding that read
Yeah.
the level of this.
What I can do is I can provide you the latest version, not the burst 3. Burst 3 is kind of like a very early code. Okay, you will not see proper, like you will not understand. It's very basics, because the people when we do there, they were also learning.
Mm-hmm.
So the code is not so advanced at that time. I can provide the latest code we use in Birds X satellite.
Bus X.
Yeah.
Oh, Bus X also using the same main OBC and DTB.
Birds X has a same reset peak. Okay. But Burst X has a different method, but reset pick code is same. I can provide that one.
But you use the same OBC board?
No, it's different because we had to change the config.
Config.
Yeah.
Oh.
So right now, if I go here, this is main pick. Is the what is the name of this one? I'll just write here. 18F 67J 94. This one 16F 1789. Okay. But the Burst X has same for the both. So Burst X, this peak also similar to this peak, also similar to this one.
Mm-hmm.
Okay. It's because it's a different. It has two transceivers. So basically, one peak cannot. This peak cannot support two transceivers. That's why we had to change it to same peak, because not enough pins. So you don't need to worry about that one. Let's go with this one. Okay.
Okay.
So what I can do is I can provide you the reset pick. Can I explain the reset pick code? You need
Yes.
maybe Monday.
Maybe yeah.
It's better I explain the reset pick code. Otherwise, you will. It's better you know that one. Other two codes you can play with those things, but not the reset pick. Okay.
So it's what's different compared to the code for main and comms?
Okay, I said you reset pick is the heart of the satellite. You cannot change anything there because it's already fixed, already tested in the space. If you do some change, that is not good. Like let's say you make simple mistake in the one line, it can cause satellite to stop working in the space. Okay.
Okay.
So other topics, no need to worry. Like you can change the code if you need, but don't change too much in the reset pick. That is very dangerous to do it.
I see. I see.
I thought the main pick is the most important.
No, it's not the important thing.
No,
Because
I mean, if compared to reset,
like okay, it's most important, okay, but if you think the satellite heartbeat and satellite nominal condition, reset pick is the one control that one, power system and everything.
okay,
You can see the problem. Okay, I'll explain the problem. Okay, let's see.
yeah.
So let's say like in birds 1 and birds 2, were there any difference compared to birds 3 reset?
Okay, burst 3, burst 4, burst 5, reset pick, everything same. Okay, and even every other satellite project same, but both burst 2 and burst 1 is a different one. You have to forget burst from burst 2 to burst 1.
I see.
So the problem with the reset, if you make a mistake in the reset pick, let's say somehow reset pick got stuck somewhere. You can see reset pick control all the power lines here. Oh, sorry. All the power lines. Let's say somehow those things cut. Everything will be disabled. Okay, then this one. Let's say reset pick got stuck, com pick disable, main pick disable, nothing is happening.
Okay.
So that's why I am suggesting please don't touch too much to that code if you don't understand.
All right.
I will try to make it understandable in the maybe Monday.
Okay.
So,
So mostly EPS is embed is reset pick
yeah,
right?
reset pick is the one monitor the EPS and control the EPS.
So it's the heart, the
Yeah.
center.
So when you touch the, let's say when you program the board, as example, when we program the satellite, let's say we detect some bug, we are very reluctant to touch the reset pick. Because
So meaning try to touch other pick lah.
yeah,
Avoid.
the problem with the reset pick is, let's say, okay, you can program, you can change the code, but you must check it very thoroughly. Okay,
Okay.
you must
Check it
keep
thoroughly.
checking like 2 or 1 month, 3 months, 2 months, like that. Long duration you have to check if you change the reset pick. Because I have seen when we run the satellite, reset pick make errors after 7 days.
Wow.
that's why we don't like to touch it.
Yeah, Mr. Mr. Tarindo, would you mind to share with us for EPS if let's say would like to do the checking on circuit on PCB board, do you have would you mind to share with us step by step from the beginning step where should we start to check this?
Okay. I can show how to do that when you program the reset pick.
Oh, okay. So okay.
So basically, I will change the reset pick code, but eventually I will go back to the old code. Okay. So what I do is in the programming, I will start the reset pick function creation, but I will go to the final code similar to the current code. Okay.
Okay.
So I can show you how to enable, disable power line, how to do a measurement, those things.
All right.
It is not so long code, it's very simple code. Another thing, okay? You should not run any very huge complicated code in the reset pick, because it must be simple code.
Yeah, understand.
Yeah, if you run like maybe let's say you are a very good programmer who knows how to do like how to write a function in 2 lines, please don't do it. So you write the most simplest functions to avoid any confusion in the code. So please remember, reset pick is the most important thing. And then other things are important. You have to make sure the other codes are running correctly, but first is reset pick, okay?
Okay.
Okay.
So maybe Monday we can do the reset pick entire code, because I have remaining things in this this circuit. So tomorrow I will explain this flash, this everything here, this config main pick, and then I will explain how to program the flash memory. There will be a small programming session also, and how the memories are allocated. Okay.
Okay.
So
Okay.
so it's better not to start something here right now, because only 8 minutes or something remaining.
All right.
All right.
Did you guys understand? Is it okay?
At
For
this
me,
moment, it's okay.
Yeah. Yeah. If you have a electronic background, so you can easily understand, but you have to check it again and again if your background is not the programming or those electronics. So please keep these things. Actually, I have not done this session even to the QTech students, so I think you guys keep these videos, okay?
All right. Thank you very much.
So tomorrow let's start from here, and the flash memory and flash memory library creation, okay?
All right. So,
Um,
Mr. Tarindu, so you plan to, for the final day, which is on Monday, you plan to like
Reset pick.
go together with us for the reset.
Yeah.
Yes. Yeah. Yeah. Okay.
I will send you the code before that one, okay? Please check that one.
Okay.
So how can I send this one?
All right.
No, how can I send the code?
you can send by email or WhatsApp
Okay, I'll send in WhatsApp. Okay.
to me.
Using WhatsApp at your place also, right?
Sorry.
It's okay. It's okay. Never.
Okay. So, okay, then see you tomorrow.
Yeah. See you tomorrow. Thank you.
Thank you very much.